Hi everyone, welcome to our seminar 3. So before we enter today's session, I would like to remind you of the deadlines of term paper. So on November 16th, you already handed in the term paper proposal. Though some people uh, I almost finished all the grading, and I also post some announcement about the repetition of data sets that you choose. Um, but I think most of people already already finished their proposal and started to work on. So this is for proposal. And on December 8th, so which is roughly 2 weeks later, you need to hand in your preliminary version of the term paper. And that means see what's your progress. And on the last session of the seminar, you need to present it. So it is on December 11th. And on January 7th, you need to hand in your final version of the term paper. And when you hand in your final version of the term paper, you need to upload a PDF file, a script file, and also a dataset that you used if it is not from ECDOT. And on December 11th, when you present your preliminary version, you will get the feedback on your work. And one thing that you need to remember is that this presentation is mandatory. So if you are not free, on that day, you need to if you are not free on December 11th, you can email me and appoint a single session of presenting the paper as well. So let me remind you again about what you should include in your term paper. So of course, the first one is a question, a topic, and then you need to mention the previous literature and studies, and then you need to explain your data set and provide some summary or descriptive statistics by using plots or tables that we taught you to produce in R. And then you need to run a regression and present the regression results. And the last part, for me, I think this is the most important part as well. So it is interpretation and discussion, because though we will only talk it like a few minutes later, but actually it is quite easy to run a regression in R. So basically since running a regression itself is not that difficult in R, so what matters is actually how you interpret the results and also have the discussion of the result that you saw when you run a regression. So I think you should focus on interpretation and discussion rather than the regression itself. Yes. So now we enter the today's seminar. So I think we already talked about hypothesis test last seminar, but I just want to remind you of how to calculate the t-statistics and the meaning of p-value as well. So t-statistics, so for example, in this slide, so the example is the difference between the average schooling of males and females. So when we calculate the t-statistics, you use the actual value that you get minus the hypothetical value. So in this hypothesis test, your null hypothesis is that the average schooling between males and females is 0. The difference is 0. So therefore, the hypothesis value is 0 here. And you need to use the actual difference between the average schooling of males and females to subtract the hypothetical value, which is 0. So which is the actual minus the hypothetical value, and then divide it by the standard errors of the schooling gap in this example. So basically it is the actual minus hypothetical divided by the standard errors that you get. And and when you get the t-statistics, then you can calculate the p-value. So the relationship between t-statistics and p-value is actually so basically you can think about that, like the p-value is the product of the t-statistics when you throw the t-statistics into the normal distribution. So if you imagine that the normal distribution is a machine, then t-statistics is the input and the output will be the p-value. So actually they actually have the similar meaning. And for the product of the normal distribution, which is the p-value, so the p-value means that, so when you get back to the way that we calculate the t-statistics, so which is the hypothetical minus, so which is actual minus hypothetical divided by the standard errors. So the p-value means that, so now we assume that the hypothetical value is true. So for example, in the slides, so now we assume that actually in the population there are no differences between there are no differences of the average schooling between males and females. So if this is true, but now when I calculate the sample and I got, for example, 5 or 4, so which means that if the population has no difference, but now I got 4, then and then after I divide it by the standard errors, then what's the probability for me to get this actual value if there is no difference? So which means that, so now, for example, if in the population there is no difference, but then you got really different numbers when you calculate the sample. So and then you will get a quite small p-value. So which means that actually your assumption in the beginning that there are no differences between the average schooling of males and females are wrong, are not that possible. So let me repeat it again. So the way that you think about t-statistics and p-value is that, so you make an assumption in the beginning, so which is your hypothesis, and then you got the actual value that you got the actual value from R. And then third, you try to see that if the assumption is right, then what is the probability that you get this value from R? And it turns out that, so now you calculate p-value, and it turns out that actually the p-value is really small. So which means that actually the probability for you to have this actual number is really, really low. So the probability is really, really low. So which means that the first step, that the first step where the thing that you assume is not that likely to be true. So this is how you think about a p-value and also t-statistics. So as stated in the slide, so the smaller the p-value, the stronger are the evidence against the null hypothesis. So which means that, so for example, now the p-value is, for example, 0.00001, almost 0, but this is the actual value that you get. So though it is 0.0001, you still get this value. So which means that the hypothesis that you assume in the beginning is less likely to be true. So this is the way that you think about p-value. So if it is the small p-value, so you can reject the null hypothesis. But if it is large, then you cannot reject it. But one thing that I need to remind you is that small p-value does not mean that the null hypothesis is wrong. So it only means unlikely. So even now the probability is 0.00001. So it can still be the case that the null hypothesis is actually true, and you are just as lucky as picking this number at this probability. So p-value itself does not really mean that the null hypothesis is right or wrong. It's only about likely to be true or unlikely to be true. So this is the thing that you need to think about the p-value. And then now we are going to talk about how to run the regression in R. So before we run a regression, we can take a look at the scatter plot of the hourly wage and experience by using LNU 91 dataset as an example. So when you run the plot about experience and wage, actually you cannot really see the relationship between them because there are lots of data sets, and actually it's quite, the data points are quite mixed together. So though you can see that there is some positive relationship since it is extend to the upper right corner, but it cannot really tell you what's the quantitative relationship between them. Therefore, you can run the regression to quantify their relationship. And to run the simple regression, actually it's really easy. So you only need to type LM in the beginning and then parentheses. And in the first position of the LM command before the slash is the y-axis, so which is the like the objective, the target variables that you are interested in, and the experience is the independent variables, so which you would like to explain and to see the relationship between the with the main variables. So after we name it, and if you want to get the summary of the regression, then you use the summary command. So just as we told you before, so the summary command is really powerful. And then if you want to get the confidence interval of the regression, then you type COFINT T, so which stands for confidence interval. And then fit is the object that you name for the regression result. And then the level, so the level is a confidence level. So in our example, it is 95%. So this is the caption. This is the picture that I captured from, this is a screenshot that I captured from the R. And you can see that, so after you do a summary of the regression result, so you can see that, so this is school, and then this is the estimate that you get, so which we will explain it later. And then this is the p-value. And then if you run the regressions, if you run the COFINT, so here is the confidence interval, 95 confidence interval. So this is how you run the simple regression in R. And then for the term paper, so if you get the data set with so when you do your term paper, if you get a data set which has different characteristics than RDA file, so which stands for R data file, then you can take a look at this slide and learn how to read other files into R. So for example, if you want to, if your data set is TXT file or CSV file, so you need to use either, you need to use read table or read CSV file. And for example, and however, if your data set is in Stata files or SAS file or SPSS files, so you need to install a library first, so which stands whose name is called foreign. So you need to run the foreign package if you use the files other than the RDA file. Yeah, so this is just like a reminder. So now we enter the session talking about the ordinary least squares regression. So we just finished teaching how to run the regression, so which is really easy. So it's only one line, so which stands for LM. But now we are going to talk about the things that behind this command. So when you run the regression, so just as before, it is wage and schooling. So you can think about y. So wage is y here, and then schooling is x here. So y is called dependent variable, so which is also your like target variables, and the xi is the independent variable, so which means the other variable that you are interested in, and epsilon here means the error term, so which is the like the difference between the difference between the predicted results and the actual results. And beta 0 is the intercept of the regression line, and beta 1 is the slope of the regression line. So this is our like target, so which is the population. So we want to know the population. However, since we cannot collect all the observations in the population model, so we instead using the observations from the samples to estimate the population parameters. So actually we cannot see this, we can only see this. So the capital letter stands for population, and the small letter stands for the samples. So the spirit of the OLS estimator is to choose the regression coefficients so that the estimated regression line is as close as possible to the observed data. So for example here, I think it will be more clear if I explain it by the picture. So the dots are the observation points, and you need to minimize. So you need to create a line which is closest to all those data points. So this is how the OLS regression works. So you need to create a line which minimizes the distance between the distance with those dots. And as close as possible in OLS regression means that you need to minimize the sum of square mistakes. So it is not only the sum, but the sum of the squared. So to minimizing the sum of square, So the distance between the line and the actual data points, so we call it the residuals. So you need to create a line which minimizes the distance between the line and the dots. And we call the line, and for us, we call the distance between the line and the dots is the mistakes or the errors. So which is also for the error term that we just mentioned in the last slide. So basically, the OLS regression is trying to minimize the sum of the squared residuals. So this is the objective or the target of the OLS regression. So which means that you need to minimize the you need to minimize the amount that the predicted values differs from the observed ones, because the dots is the thing that you actually saw or collected, but the line is the thing that you calculated. So you need to minimize the difference between the actual and the calculated ones. So in assignment 4, so which is also the question 1, you should be able to formally derive the OLS regressions intercept and coefficient B0 and B1 respectively by minimizing this function. And to find the answer, you need to be able to do the some simple calculus. And I think you can find it on the textbook. And after you do the calculation, you should find that. So the intercept, so which is the intercept that we just mentioned, so the beta 0 or the B0 is the average value of dependent variables minus B times the average of the independent. And the B1, so which is the slope, is actually the covariance between dependent and independent variable divided by the variance of the independent variable. So this is the relationship of B0 and B1. So since we get this value, and then how we can see this the relationship on R. So now here comes the new command. So after we run the regression, so which we ran it a few minutes ago. So actually we can plot relationship and also add the results which we run of the regression. So we use the plot. So let's get back. So how are we going to show the thing that we run, or how are we going to show that actually the relationship of the intercept, the relationship between the intercept and the average value of dependent variable and independent variables? So how are we going to show the results of those things in R? So so we will use the example of the regression between wage and experience again to show it. So first we use the plot. So you are already quite familiar with plot, right? So first we use the plot and we plot experience and wage. So the PCH here is how we So PCH here is to adjust the way that you present the data points. And then the XLab and YLab is the name of the x-axis and y-axis. So, but basically this is the plot comment. And then now here comes the new new command, so which is called apply. So apply is to add a line in your plot. So basically this is the function of apply. And then you type apply fit, comma, LWD equals 2. So LWD stands for the line width. So which is the width of like how wide your line is. So this is to adjust the width of your line. And then fit, so the fit comes from the objects that you name for the regression result. And then next, we still use the apply function to add a red line for the mean wage. Sorry for the typo, so it should be mean wage. And also for a green line for the mean of experience. So since wage is on y-axis, so the mean wage should be a like the should be a horizontal line, right? So H here stands for the horizontal line. So we add a horizontal line for the mean of wage, and then we adjust the color of the line. So we should be, we use it red, and then the LTY here. So LTY here is for the line type. So you can make it like a straight line or solid line or dot line. So LTY equals 7. Here is the solid line, so which is a default. And so we also draw a green line for the mean of experience. So which means the experience is on the x-axis. So the straight line for the mean of experience should be a vertical line. And then we put a color green for it. So next, we would like to show a red circle of the intercept. So we use the points command to show a point. And then, so when we draw the intercept, so when you run the regression, so let's turn back. So when you run the regression, so you can see that in the coefficient. So here is the intercept. And the estimate here is, so the first coefficient that will show in the coefficient. So the first position that the coefficient will show is the value of intercept. And then the second position of the value that the coefficient will show is the value of independent variables. So that's why here, when we state the position of the points for the coefficient, for the intercept, so that we type 0 and then the coefficient fit 1. So the coefficient of fit, so fit is the regression. And just as I mentioned, so the first position of the coefficient of the regression is the value of intercept. So we type the first position here. And then PCH here is also for the type of dot, and then the color, also the width. And then the text is the similar. So the text is to add a text on the plot that you would like to draw. So you also need to tell R, so what's the position that your text would like to be added. So I would like to edit the intercept under the dot that I draw. So I also need to type the position of the dot. And then the adjacent, so is to adjust the distance between the dot and the word, and also for the color. So this is how we draw a red circle for the intercept. And then the next is to place a blue circle at the mean point and mark it as mean X and mean Y. So which is similar. So also use points and also text. So which is similar. So now you need to change the value of points to mean of experience and also mean of wage. And then the text is sorry, so there is a typo. So for the text, so the first two positions should be the value, and the thing with the double quotation mark is the text that you would like to add around the values. So which is similar when you try to show a red circle with the intercept. So after you do it, then you will see the following picture here. So this is the regression that we just run. So the wage, okay, so now we can see that, so this is a result after we execute those commands. So wage equals 46.8338 plus 2.488 times experience. So the horizontal line is the mean of wage, so which stands for Y. And the green line, the vertical line, stands for the value of mean of experience, also the mean of X. And then the black line, black straight line here is the fitted line, so which is also the regression line. So you can see that the black line goes through the blue dot, which stands for the mean of wage, also the mean of experience. So which which proves the result that you calculate from the algebra or the mathematics, that the regression line should go through the mean of the dependent variable and the independent variable. And then another thing is that, so the red dot here is the intercept. So this is the results when you calculate by using those commands. So which is also proves the results if you use the mathematic or the algebra to prove the regression. So basically, this is how we do the regression. And then another thing is, another concept that we would like to introduce you today is R-square. So R-square is, wait a second. So now we are going to introduce you R-square. So first I will talk about how we understand the R-squared, and then I will talk about how to calculate it by hand. So R-squared is the fraction of the sample variance explained by the regressor. So which means that how powerful that your regression can explain your variables. So the way that we calculate it is to use the explains sum of squares divided by the total sum of squares. So the total sum of squares is basically the difference between the squared difference between the actual observations and the average values. So you can see that here. So this is the actual samples minus the average. So this is the total sum. And then the explained sum of squares is the square difference between the predicted values minus the average sums, minus the average values. So just as we said, since the so why we calculate it like this is because since the so you can see it from the picture so that you can understand better. So the total sum is the difference between the object. So it's between the actual value minus the average value. And then the explained one is the predict values minus the average values. And since we know that, so you can see that the axis here is not the y, is not simply the x-axis, but the value of average of y. So the difference between the axis and the actual value here is the total difference. And we know that, so the regression line will go through the mean of x and also the mean of y, right? So here is the mean of x and the mean of y. So this part is explained by the regression results since it successfully predict the values of here. So this is the segment that the regression explains. So which is also stands for the definition of R squares. So this is the part that the regression successfully predicts or explains. So you use this segment divided by the total, so which is the R square. And then we take back here. So this is the explained sum of squares and also total sum of squares. But there is still another way that you can calculate for the R square. So which is that you use 1 minus the residual sum of squares divided by the total sum of squares. So what is the residual sum of squares? So the residual sum of squares is the thing that is the difference between the actual value and the predict sum. So if you look from the picture, so which is the difference between the actual one and the predict one. So this part does not, so this part is not explained by the regression. So which is also means that actually this part is the residuals, or you can call it error term as well. So which actually is related to the thing that we just mentioned when we introduce the OLS regression in the beginning. So this part is the thing that the regression cannot explain. So if you use 1 minus the residual sum, which is the thing that cannot explain, and the remaining part is then the parts that the regression can explain, right? So if you already subtract something you cannot explain, then the remaining part is the thing that you can explain. So this is how we calculate the R square. So let me say it again. So the total sum of squares is the difference between the actual and the average. And then the explained part is the predict minus the average. Since we know that the average values of the variables must be on the regression line. So the difference between them is then explained by the regression line. And then the residual is then the actual minus the predict. So this is the error or the residual. So this is the graphical explanations. So if you feel a bit difficult to understand what is the meaning of R squared, so you can think about of this picture. So R squared is the fraction of the sample variance explained by a regressor, just as we mentioned. And one thing that you need to keep in mind is that, so R squared must be between 0 and 1. So because either you cannot explain the variation at all, or you can explain it. You can explain it all. So the extreme value of the R squared is that the explained part is equal to the total sum part. So it must be 1. And the variance that you can explain at the least is that you cannot explain anything. So it should be 0. So which means that the R squared must be positive. And if R squared equals to 1, so it means that all the variation in Y is explained in the model, so which means that perfect fit. And if R squared means 0, then it means that no fit at all. And then now we enter the multiple regression. So we just show you how to run the single regression net, right? So actually the way that you run the multiple regression is also quite easy as well. So you just need to add addition notation behind the variable that you would like to add. So I just run the regression. I just run the regression. I just run the regression of wage and experience, right? So now I would like to add school and female, and I just add like plus school and plus female. Then this is the result when you run the summary of the regression. So this is how we run the multiple regression. And then in multiple regression, so the R squared increases whenever a regressor is added, unless the estimated coefficient on the added regressor is exactly 0. So what does it mean? So when we turn back to the definition of R squared, so R squared is the fraction of the sample variance explained by the regressor. So which means that naturally, when you add more and more regressor, then the variance that you can explain, the variance of the dependent variable that you can explain is naturally just becomes like more and more, since you already add more and more variables. So the thing that you can explain for a dependent variable is of course increasing. So since in practice, it is unusual that the estimated coefficient will be exactly 0. So which means that the new variable, it's quite rare that the new variable that you add cannot explain anything, any variance of the dependent variable. So it means that in general, the R square will increase when you add more and more variables. However, this actually violates the original ideas of R square, because because the purpose of R square is to know that how much the variance that can explain by the variable that you put. But if the R square just increased naturally when you put more and more things, then actually, which means that the R square is biased by itself, because it means that once you can put, for example, 1 million variables in a regression, then the R square will naturally becomes 1, or like near 1, 0.9 or something like that. But this is not the original idea for R square to like this is not the original idea of creating R, this concept. So as a result, one way to correct for this inflated estimate of fit. So one way to correct it is to reduce the R squared by some factor. So we need to add a corrected term or a corrected multiplier in front of the thing that we calculate. So the original R squared for single variable is that we use 1 minus the residual squares divided by the total sum of squares. And now before the residual and the total sum, we add a corrected term, a corrected multiplier. So it's n minus 1 divided by n minus k minus 1. So n is the total variable, and then k is the independent variables other than the main variable that you would like to put. So for example, in the slides, so here are 3 variables, right? So the n is 3. So n is not the variable that you put, so that means modify it again. So n is the numbers of data points that you add. And then k is the variables that you put to explain the variance. So in this example, so we know that there are 2,246 data points in LNU dataset. And then here are 3 variables, independent variables, to explain the variance of wage. Then here n is the 2,246, and then k is 3. So the corrected multiplier will be 2,246 minus 1 divided by 2,246 minus 3 minus 1. So this is the idea for adjusted R squared. And the last thing that I would like to mention is the logarithm in regressions. So as well as in the assignment 4, so one of the questions is what is the meaning of putting a logarithm in the regressions? So let me explain a bit. So when you put the logarithm in the independent variables, so in the x part, so which means that when the x, so for example, if you put okay, so for example, when you run the regression between wage and experience, when you put logarithm on experience, so which means that if there is 1% increase of the experience, then what will be the change? Then there will be a change of the wage of the 0.01% of the coefficient in front of the experience. And if you put logarithm in wage, for example, like in y, then it means that if your experience increased by 1 year, then for example, if the beta 1 equals 0.06, then which means that if your experience increased by 1 year, then your wage will increase by 6%. So which will be 0.06 times 100%. And if you put both of the logarithm on x and y, so which means that then 1% change in x is associated with the beta 1% change in y. So which means that beta 1 is actually the elasticity of y with respect to x. So for example, if you want to know that the elasticity between wage and experience, then you can try to add both of the logarithms on wage and experience. So so the thing that I mentioned today are all related to the assignment 4. And if you have any further questions, just feel free to email me. And that's it. So thank you for your listening.